Okay, so I guess you can see my screen. In the last class we have just briefly discussed how to run the pushover analysis. Today we will learn in details what is the background of pushover analysis and what are the different things you need to know when you are trying to do this analysis. Okay, so first let us start with the code book, which gives the criteria for pushover analysis like modeling parameters, which is ASC 41 2013. Actually, latest version of this code is ASC 41 2017, but we'll start with 2013 because the parameters defined in this code is little bit simpler compared to the latest version. And in the ETAB also we are going to choose the parameter according to this code only. Okay, so you have to refer chapter 10 of ASC 41 2013, which is for concrete structure, which means including RCC, not plain concrete only. Here you see our structure is a bare frame structure which consists only beams and columns. Okay, so here we are going to find the modeling parameter, which is criteria for which is given in ASC 41 2013, and let's see what are the parameters and how they are defined. Okay, so these are the curves first we have to understand. So as you can see in the first curve, this one, in the x-axis this is given as theta or delta, means rotation or deformation, and in the y-axis you can see this is q by qy, means normalized value of forces. It can be either force, lateral force or moments. Okay, anything. Now let's say we are trying to develop this curve using force and deformation, or you can see using movement and rotation. Okay, so you have to take the normalized value and see the parameters what is given here: A, B and C. Okay, what is A? If you consider this as the yield point where your structure or member is going to yield, from that point to this point. This point means what? You can say this is the point beyond which the structure loses all its capacity. Suddenly the capacity will be reduced drastically, and it will reach to this point where it has some residual capacity left out. Okay, so the distance between this yield point and this collapse point is called denoted as point A, sorry, parameter A. Then see the parameter B, from the yield point to the maximum deformation level. So this is the point at which the structure completely collapses. Okay, beyond which the structure will not be able to survive, it will be completely damaged. Okay, so this till this point, this is point B, and C is the residual capacity. Okay, this is the capacity which is always present in the structure even if it fails, still before the complete failure. Okay, and these are the curves similar to this one, but with some differences. As you can see here, this is in terms of drift ratio, here it is in terms of rotation or deformation, here it is in terms of drift ratio. Okay, and this is another shape of this backbone curve. This curve is actually called backbone curve. So here you can see this is after yield, this is just this is a bilinear curve, as you can see here till this point C, but here it is trilinear curve. So this code has defined both the possibilities. Actually, usually we go for this one, this bilinear shape. Okay, now we'll see what are the parameters given in this code. So in this table you can see at table 10.7 modeling parameters and numerical acceptance criteria for nonlinear procedure for reinforced concrete beams. So these are the parameters defined in case of beams. Okay, so what are the different parameters? Here you can see plastic rotation angles A, B and residual strength ratio, as you can see that is C. Okay, so the three parameters what we have just discussed now, and these parameters depends on this rho minus rho dash divided by rho balance. Let's see what is this rho minus rho dash. This you can see in the index. Okay, so rho is the ratio of non-pre-stress tension reinforcement. It means the tension reinforcement ratio. Okay, then what is rho dash? It is the compression reinforcement. Okay, so this is tension reinforcement minus compression reinforcement divided by balanced reinforcement, rho balance. Okay, so you have to calculate this ratio. Then this is B is the shear force, B W width of the member, D is the depth of the member, and FC dash is your grade of concrete, compressive stress. Okay, so based on these parameters you can calculate this. Then depending on the value of these, now you see whatever value you get, for that the based on different ranges. For example, if this ratio is between 0 to 0.5, okay, and here you see transverse reinforcement C, it is basically ductile or non-ductile. Okay, C means conforming and C means non-conforming. So conforming means it is ductile and C means non-conforming or non-ductile. Okay, so if suppose your this ratio is between 0 to 0.5 and we are considering ductile structure, and this range is between 0.5 to 0.25. see again inside the bracket this is in this MPa, megapascal unit, and this is in FPS, means this one pound per inch square in that unit form. Okay, so you have to refer the values which is given inside the bracket. Now based on these values you can identify what should be the value of A, B and C. Okay, and this is immediate occupancy, and this is life safety, and this is collapse prevention. Okay, this I'll explain now. Okay, before discussing, let's try here what is given the definition for these parameters in the code. Okay, let's discuss. See, IO means immediate occupancy. It means this is the stage where the building, means after the earthquake, when the building is subjected to earthquake, and post earthquake the stage of damage in the building. So what happens within this stage? If the building is there, this means this building is still fully intact, the building is not damaged, and it can be occupied immediately after the earthquake. Okay, so this is the immediate occupancy, and this code ASC 41 defines if where is that table? So this rotation, let's say our reinforcement ratio falls in this range. Okay, and accordingly, say this is our IO value we have obtained. Okay, this is the limit actually, and for example this limit is coming somewhere here. In horizontal axis we have this rotation theta. Okay, so this limit is given in terms of rotation, plastic rotation angle, as you can see here. Okay, so now after the earthquake we have seen that our building is rotated within this range. If we say this is 0.005, the building has not rotated by this amount, it was less than that in this region. Okay, so we can say the building is fully intact and it can be occupied. It means the earthquake has not affected severely to the building, so building can be used immediately after the earthquake. This is the meaning of this range. Similarly, next you see this is LS, means life safety. What is the meaning of life safety? So as you can see, the LS rotation is more than the immediate occupancy. Okay, so somewhere here you see, let's say this is IO, this is LS. Okay, life safety, by the term itself you can understand, means there is no threat to the life. Okay, so there is no possibility of any casualties, but there can be some damages, some minor damages, some member may be failed, but the building will not be fully collapsed. Okay, and there will be no severe structural collapse also if suppose some one or two columns failed or one or two beams failed. Okay, like this some members may fail, but structure will still be intact. It will be able to carry the loads, but some failures will be there. Okay, and due to this there will not be any chances of any casualties or death. Okay, so this is the meaning of this life safety stage, and accordingly code defines this is the maximum rotation within which if the building is there, then you can say it is within the life safety stage. Okay, next, collapse prevention, and this is the again the rotation limit given by the code for this. So let's say here this is the collapse prevention. So again by the term you can understand this is something related to the collapse. So we can understand like this, within the, means just before this point here the building is not going to collapse, but if we exceed this limit we can say building is collapsed. Okay, so this is the limit of this collapse prevention beyond which we are not allowed to go. Okay, so now again, so you understand, after the earthquake if the rotation is within this limit, so you can say the building is not collapsed, but if the rotation is with beyond this limit, rotation is exceeded, so you can say it is going to collapse. So these are the limits given. Now how these limits will be used in our analysis? We'll give the limit, we'll give this IO, LS and CP in the software, then we'll compare after analysis where our actual performance of the structure or performance of different members comparing with these values. Okay, for example, after analysis I'll check each and every beam, the rotation occurred in the beam, I'll compare with this. If suppose the rotation occurred in the beam is less than this, so I can say the performance of that member is within IO. Okay, or suppose the rotation exceeded this value but it is less than this, so I can say the performance of that member is between IO and LS, like this. So to check the performance stage of the structure we'll use this IO, LS and CP. Okay, and this backbone curve actually I have also discussed in the last class. Again I will just give a brief about this. Suppose you have one column and you are applying lateral force here. Okay, so what you will measure, you will measure the deformation and moment or force deformation. Okay, now let's say in y axis I have force, in x axis I have deformation. Okay, so you are applying the force and measuring the deformation. So for example, at this deformation level I have applied this much of force, so I have one point here. Then at this deformation, let's say I have this much of force, so I have this point. Then let's say at this deformation level the capacity force which can be carried by this member is reduced. Okay, let's say this is the point. means this much force can be carried at this deformation, so structure is going to means structure is failing slowly. Okay, so if you join these points something like that. Okay, so this is your backbone curve, and this can be determined for each and every member depending on the reinforcement, how much reinforcement you have provided and what is the section size you have provided. So you can determine this. That's why code gives this criteria. This criteria depending on the reinforcement and depending on the dimension of BWD, as you can see, and also the grading of concrete. Okay, so based on this parameter, if you do not want to analyze the member every time to determine this, so you can directly use the parameters given in the code. Based on this ratio, how much reinforcement is provided by you, and the size or dimensions and grading of concrete considered for your analysis. Okay, so based on this parameter, directly using this table you can calculate these values A, B and C, and also IOLS and CP. Okay, so this is for beam, RC beam. Similarly, you can also determine for RC columns. This table is for columns. Modeling parameters and numerical acceptance criteria for nonlinear procedure, reinforced concrete columns. Same parameters A, B, C, IOLS and CP, but for column. Okay, so in case of column C, what are the governing parameters? P by AGFC. This is axial load ratio. P is the axial load, AG gross area, and FC is the grading of concrete, and rho is, I think, ratio of transverse reinforcement. So this is the area of the transverse reinforcement. This is BW, width of the section, and S is the spacing of reinforcement, I think. Let's check, I am not sure. So BW is the width of the member, or here it is web width in case you have some flange section. And S is the spacing of shear reinforcement. Okay, so again, based on this, how much you are getting based on this, you can calculate these parameters. Now see where these parameters will be used in our software. Okay, last class I have shown you running the pushover analysis using default hinges. Means we did not define our own hinges, we have just used the hinge which is available in the software automatically. Okay, so today you'll see how to modify the hinges and how to define the hinges. Okay, so this is the model which we have run last class, so I think the hinges are already defined. Let's check. So hinges are defined as you can see here. We have defined two hinges for each member. Okay, one at in case of column, one at top and one at bottom in case of beams at both the ends. Okay, at a relative distance of 5% from both the ends. Now let's check inside what are the details available for each of the hinges. Show generated properties, and see this B is representing the hinge for beams. Similarly you will also have columns, okay, which is represented by C with some other numbers. Okay, let us first check for beams. Modify and see, this is the backbone curve given in the defined by the software when we have chosen the default hinges. Okay, so software automatically defines everything. Here you can see immediate occupancy means IO, LS and CP. So the values which is defined by the software is 0.01, 0.025 and 0.05. If you check on the code, that was for beam. So if you check on the code, .01, 0.025 and 0.05. This it means there is rho minus rho dash. So this is tension reinforcement minus compression reinforcement divided by balance. So basically it means, I think there is only one side reinforcement is provided, so this ratio is going to be 0. Okay, and also this ratio is less than 0.25, so software is considered this limit. Okay, and accordingly your A, B and C will be this. Now let us see what the software is provided. Okay, so see this A, B, C, what is defined here, that is not similar to the one which is given in code. Okay, you have to understand from this curve. So this point is going this pink color, pink or some orange color, I think pink color. So this is point A, and this is point B, and I think this is point C. Yes,
वो आप बिल लेके आना है जी, वो
हाँ
वो हो गया, आप ले लीजिए।
आप लाके ठीक है, मैं बाद में चेक लेता हूँ।
मैं तो आपको वहाँ देखने के लिए गया था।
अच्छा,
साइड में।
अरे कोई नहीं।
तो हाँ।
अच्छा, नकली जी है क्या वहाँ पे? नकली जी नीचे आलोक जी बैठे हैं, उनके पास से मेरा एक बिल है, वो लेके आइए। Okay, so this 1.1, 0.2 and this is also 0.2. Let us understand this with the help of one example here. So what is taken by the software, so this is 1. Okay, why it is 1 is, if you look at the this curve here, okay, or this one, this is the normalized value. Okay, so where software is normalized in terms of field strength. Now for this point, as you can see, this is 1 and it is normalized in terms of field strength. So at this point this Q will be Qy. Okay, so this value is going to be 1. That's why the first, you can see this is 1 at point B, so this is point B. Okay, then 1.1, so this is 1.1, this one. If you have some q here. Okay, this q divided by qy, so that will give 1.1. okay, then 0.2 at this point, so it is reduced. So the q at this level divided by qy, so this is 0.2, and again at this point also it is 0.2. okay, then rotation corresponding to this point, at this point corresponding to b, corresponding to this point b, here you have some rotation, but if you look at the software it is considering 0. okay, so why it is 0? Because this is the complete rotation, not plastic rotation what is defined here. okay, but software is considering in terms of plastic rotation. okay, so plastic rotation, the rotation beyond this point, this is the plastic rotation, and inside this is going to be, this range is going to be the yield rotation. okay, so if you start from this point your curve, so at this point your rotation is going to be 0. okay, because at this point there is no plastic rotation, it starts from this point, so at this point it is 0. okay, that's why the first reading is 0 here, this one. Then next point, okay, sorry, this was the first point, origin. okay, so that's why this is 0 0 for both movement and rotation. Then this point also in the same line, that's why here it is 0. okay, then this point, at this point you have reading 0.024. now this, let us compare with the code. This is 0.025. okay, and software is considered 0.02448, so this is almost 0.025. so again here what the code has given, this is some empirical limits they have given, but the software what it is doing, based on the analysis of your section, based on the actual reinforcement provided, software has calculated these values. so there can be some variation with these values in comparison to the code book. okay, or else you can directly go for the values which is given in code book based on the limit of your reinforcement and sections. okay, so this may not be same as given in the code, but there will be some similarities. the changes or variation will not be drastic. As you can see there, it was 0.024 something, here it is 0.025. then at point B, means if you compare this limit with point B, I think someone is trying to get entry. okay, see here, this is 0.024 or 0.025, you can say 0.0247, so almost 0.025. okay, but in the code you can see second limit is 0.05. okay, so you can ask why this much variation. To understand this, again you have to go back to the backbone curve. Here you see the B limit is till this point. okay, from this point to this point, but software is given the limit up to this point. okay, so you have to deduct this much to get the value which is given in the software. okay, that's why there is a difference. Then at the end, at this point, this is given as 0.0479, or you can say 0.048 or close to 0.05. okay, so this you can compare with, now you can compare with this B, because in the code book the value given till the end of the backbone curve is B. okay, so this you can compare with the value given in the software. So this is 0.05. Now see in the software how much given, 0.0479. so this is almost close to that. Okay, and what about C? C is this residual capacity that was given in the code book as 0.2. See in the software how much it is, this one 0.2, 20%. Okay, similarly this for compression, similarly you can, sorry, this is for tension side and this will be for compression side, concept is same. Okay, and this moment here shown, it is the yield moment with which this curve is normalized. Okay, it means all the values are divided by this for the positive axis and by this for the negative axis. So this is going to be the capacity which you will get from the section analysis. In the section designer you will define the section, then you will analyze the moment curvature, and the moment yield moment what you are getting from moment curvature analysis will be this for the positive axis and this for the negative axis. Okay, so with respect to these values your backbone parameters will be normalized, as you can see here. Okay, and this I think you understood already, we have explained. So this is for one of the members. Similarly you can check the hinges for other members. Let me take another random, any of the hinges. So the shape will be similar and this will be constant, because everywhere with respect to this only we will determine the rotation. This rotation can be same or it can be different depending on which section we are taking. Okay, if the section size and reinforcement are same, so these values will be same. If your section size or reinforcement different, these values will be different. Okay, so like this you can define your own hinge. Sorry, I didn't show you how to define your own hinge. Let me now show you how to define own hinge. Okay, so instead of going for this one, you can simply define a add new property concrete and OK. Here you can define your hinge name. Let's say beam hinge, and here you'll select which type of hinge you are going to define. Okay, can anybody tell for beam what kind of hinge we need by looking at these details? Think, in case of beam, what are the things you usually take? Okay, let me ask, in case of beam, are we considering axial force? No, right? We can are we also going to consider shear force V2? Okay, someone said, Ivansh said no. Yeah, in case of beam we do not consider axial force. Then what about shear V2 in case of beam? This also I have explained in one of the class. If suppose this is your beam, you have two axes. This is one axis, this is another axis. Okay, so you'll have shear in this direction, which is V3, sorry V2, this is V2, and you have shear in this direction, which is V3. Okay, so now say, tell me which shear we consider in case of beam. You can type in the text box if you do not want to speak. Let's say this is the frame structure you have, and this is the beam. If you look at the 3D view, like this, let's say, okay, and these are going to be your axis, this is y and this is x. So what I'm saying, this is your V2 and this is your V3. So horizontally if you say that is V3 and vertically if you say that is V2. Okay, now can you tell me which V we consider in case of beam? Someone said V2. Is there any other answer other than V2? Okay, Akshay said V2, that is correct. In case of beam, we consider the shear force in the gravity direction. Okay, so accordingly, where was that? Here, if you want to define shear hinge, okay, means you are considering the structure can also fail in shear. Okay, so if you want to define the hinge for that type of failure case, you can define shear V2 in case of beam. Okay, again accordingly you can define these parameters. Thank you. Okay, so this was the case for shear hinge. Now suppose I want to define the flexural hinge, means I want to consider the failure by bending moment. Okay, so you have M2 M3, then M2 M3 combined, PM2 PM3 PM2 M3 and so many. Okay, then fiber PM3, this I will explain later on, not now, including this parametric. Okay, so ignore these cases and consider up to this in interacting PM to M3. Okay, so from these many cases, can you tell which type I have to consider if I want to define flexural hinge for beam? You can type here if someone has any idea about this. Okay, Nishant said M3, Akshay said M3, anyone else? Okay, so that was right, Akshay and Nishant. In case of beam, we define the flexural hinge by M3 if we consider uniaxial failure case. Okay, so again, what is uniaxial and biaxial? Let's see. If suppose you have the section like this, so this is going to be your y, this is going to be x, means this one only I am just drawing separately. and this is the structure. Let's consider. Now if you push from this direction, this structure, if you push from this direction using some lateral force, okay, so this structure will deform, and movement is going to be generated here, like this or like this. Okay, so now you see this is M3 basically what we define. This is M3. But another way movement can be generated. This movement what we have shown here, this movement is with respect to x-axis or about x-axis, you can say. Similarly, movement can also generate about y-axis, but there is no possibility of generating movement about y-axis when we push our structure using any lateral force. About y-axis movement can generate only if there is any torsional case. Okay, you are applying the torsion directly to the structure. That time the movement can generate in case about y-axis also. Okay, now let's say we do not have any such loading, so we'll consider only movement about x-axis or M3. Okay, so here for defining the flexural hinge, you will select this one M3, and here these parameters will be defined. Okay, as I have told already, for determining these parameters you can either use the ASC 4113 code directly, or you can analyze your member in section designer, then you determine the moment curvature curve and you determine these values. Okay, and this IO, LS and CP anyhow you are going to take from the code ASC 4117 based on the criteria given in the code. Okay, so this is how you can define your own hinge, and this hysteresis types and parameters, this is some advanced topic, will not discuss now. Okay, as you keep means you start your actual structure analysis, then you will come to know slowly about these parameters. So this is for beam hinges. Similarly, let's see what is there inside in one of the column hinge. So here you see something is written which is hidden here actually, interacting P, M2, M3. Okay, basically PM interaction curve M2 and M3, so both the direction considered. In case of column you have also done the PM interaction curve considering both the axes. Okay, and P is the axial force, and here you see what are the different axial force considered in the software. Only two axial force limit is considered here, 400 and 1600. So software is considered only two values, but when you are defining your own hinge, then you can consider as many axial force as you want. Okay, 10 axial force, 15 axial force, how many you want you can consider. But remember, as you are increasing the number of axial forces, your hinge is going to be more complicated, so software will take more times to analyze. Okay, then modify show angles. Okay, so this means these angles, as you can see, 0 degree, 90 degree, 180 degree, 270 degree. So when you are defining, usually when you have manually determined PM interaction curve, let me erase all this. When you have done PM interaction curve for your section, let's say this is the section and this is x-axis, this is y-axis. So what you have done, you have determined for x-axis and y-axis only, means 0 degree and 90 degree. But what about this some random axis, about this axis you have not done. Let's say this angle is 30 degrees, so you haven't done for any angle within this 0 and 90. Okay, so in the software it gives this condition also. If you want to define the hinges for other axis at any random angle, you can also do that. Okay, so the by default software is considered this many axes. As you can see, between 0 and 90 it has considered 22.5, then 45, 67.5. so within this axis 0 to 90 it has considered 3 more axes. Okay, so like this you can do. Then see moment rotation curve details. Here you see this is the axial force. Here you can select for which axial force you want to check, and with respect to this axial force, for what angle you want to see. You want to see for 0 degree angle, you want to see for 22.5 degree angle, you want to see for 45, like this. Whatever angle you want to check the values you can choose here, and accordingly you can see here. Okay, then if you want to select if you want to check for some other axial force, so you can select, and accordingly you can change the angles for what angle. So as you see here, the hinge definition for columns is complicated compared to the beam. In case of beam, there is nothing like angle or axial force. There is only one case where you define simply the values only one time. But here you see the number of times you have to define the parameter depends on how many axial force you are taking and how many angles you are considering. Okay, so each and every time you have to define if the values are going to be different. Okay, for each of the cases, again, immediate occupancy, life safety, collapse prevention, this you have to define. The concept is same. Okay, so these are the angles. At what angle you want to view your PM interaction curve. So nothing important, just this is for observation purpose. Okay, so that's it. Like this you can define your PM interaction hinge for columns. Similarly you can also define, okay, I didn't show how to define the hinge manually for columns. So again, similarly considering concrete, then okay, so here you'll select PM1 M2 sorry PM2 M3, then you'll define this, how many axial force you want. You will define, for example, I want axial force of I think here I have to enter the axial force minus, let's say 1000 kilonewton I want. Then how to increase. Okay, here I have to give how many numbers of axial force I want. Let's say I want 5, then enter. So 5 rows and columns are there. Now you can edit this. So I want for 1000, I want for 1500, I want for 2500, let's say. I want also for 3000, let's say. So this is for compression. I also want for tension. I want for, let's say, 500 in tension, then 500 in 1000 in tension. So like that, whatever values you want you can enter here. Okay, so accordingly it will be reflected here, how many axial force you have defined, and how many angles you want. Again you can increase number of angles where I can edit. Okay, so this point have to be changed. As you can see, the first it is already selected here. Moment rotation dependence is circular. Okay, it means it is circular irrespective of the angle, means whatever angle you consider, the values is going to be same. Okay, that's why it is considering automatically only one angle if you select this option. Okay, now if I select this one, this option, moment rotation dependence is doubly symmetric about M2 and M3. Okay, so you will have one value with respect to M2, you will have another value with respect to M2. So M3 it will be reflected in the opposite direction also, and this M2 will be reflected in the opposite direction. Okay, and it is going to be symmetric. So in this case you will have only two values. Okay, one is at 0 degree and one is at 90 degree. Now if I select this option, moment rotation dependency is no symmetry. Okay, so this means the values can be different at different axes. In this case you can define how many angles you want here. Okay, for example, if you want 16 angles, you can enter 16 and you can type all the different angles. So software is automatically calculating 16 angles. Okay, now if you go inside here, these readings you have to enter for each and every combination. For example, I want to define for 500 axial force, and for each and every angles how many you have defined here. Then after filling all these details, then you will change the axial force, and again for each and every angles. So like this, how many you are defining for each and everything, you have to enter the values here. Okay, similarly this also, by default something is given, you have to check whether it is correct or not. If it is not, then you are going to modify these readings also. Okay, so like this you can define the hinges for columns. Okay, so this was about the definition of hinge manually. Now suppose you do not want to define the hinges, instead you want to modify the hinges which is given in the software. For example, this one, this is given in the software, not given means we have chosen the default hinge which is provided by the software, and now I want to modify this. What you can do, you can just convert this auto hinge to user property and modify. Okay, now you can modify these readings if you want. For example, I do not want this hinge to be like this, instead I want to connect this point to this point straight away. Okay, so what I'll do, this readings I'll change, I'll make it to this readings, sorry, not this readings minus 1.1. so this is changed here, as you can see. Similarly this also I'll change. So now you can see, so I can modify however you want, how much you want to modify, which data you want to modify, you can do. Okay, so this is also possible. Similarly you can do for columns also. So this was all about the hinge definition. If you have any doubt, you can ask me, otherwise we will move to the next concept. You can ask if you have any doubt anywhere in this hinge definition. Okay, if not, we'll run the analysis and we'll discuss the result once again. Okay, so analysis is over. Let's see the result. You can see here shear force versus displacement, and this is the pushover curve for x direction. Okay, let us extract this in Excel and after that we'll discuss. So here you see, this is the displacement column, this is the shear force, and here see something is given A to B. So this A to B is the range given as provided in the backbone curve. Here A to B, B to C, C to D, D to E. Okay, so how many hinges performing within this range, how many hinges performing within this range, how many within this range, how many within this range. So these are given in this. Okay, A to B, B to C, C to D, D to E, then greater than E. Greater than E, if you see in the code, this is complete collapse. Okay, so greater than E, wherever you see, you can understand this beam is completely failed. Okay, then range is also given in terms of A to IO. So you have also defined immediate occupancy, life safety, collapse prevention. So range is also given with respect to that, how many hinges within this range, point A to IO, then IO to LS, then LS to CP, then greater than CP. Okay, so we'll just look into this and see how many hinges performing within this IOLS. If you see this row, from this point, means from this displacement level at the displacement of 137. Okay, so before this displacement all the hinges are within the IO level. So what it means, if suppose one earthquake happened and the structure is displaced by 130 mm, let's say. Okay, so we can say at this displacement all the beams and columns are intact, they are not failed. Okay, as you can see up to 137, not up to 130, let's say up to 131, all the beam hinges or column hinges are within the IO level. Okay, so we can say the structure is intact, it can be used after the earthquake. But beyond this 137 limit, at 137 you can see 11 hinges are crossing this IO level. So it is now beyond IO and within LS, you see 11 hinges. So as the displacement increase, number of hinges are also increasing, and you can see at this displacement, 20 hinges are, 1 minute. Okay, now you can see at this displacement, this is the displacement of 354, 20 hinges are crossing the LS limit and it is moving towards CP, but not yet reached the CP, but it has exceeded the LS limit. So what we can say, before this displacement, let's say this one 354.65, so up to this displacement all the hinges are within LS limit, it has not exceeded the LS, but beyond this displacement the hinges are exceeding the LS limit. Okay, then at the end, means where the analysis failed, the structure is now performing within the LS and CP, but the analysis could not run beyond that, so we cannot say whether it is failing completely or not. Okay, so up to the CP we could observe, beyond that the convergence failure occurred, so we cannot say anything what is happening beyond that. Okay, now like this, after running the pushover analysis, you can analyze the performance of the structure by looking at these readings. Okay, and you can also observe the pushover curve. So this is your pushover curve, and now you can do some research on this pushover curve. You can determine your yield base shear, you can determine ultimate base shear, and you can determine the ductility, how much ductility you have, how much overstrength you have, and what will be the response reduction factor you are getting from this pushover curve. All these things you can analyze from this pushover curve. I don't know whether these things are explained or not in the class. If not, sir will discuss all these things, and after that you can keep on, means you can practice with this curve after analyzing your pushover curve. Okay, now if you have any doubt here or anywhere in the discussion, you can ask me. Anyone having any doubt? Okay, so this was for x direction. Similarly, you can check for y direction also by clicking here. Okay, I think in this case we did not run for y direction. You can run the analysis, and after that it will observe here, and you can accordingly check pushover curve for other direction also. Okay, so this is all about the pushover analysis, and today we'll stop here. After that, one more concept, time history analysis, is remaining. That I'll start once sir introduce this concept in the class. Okay, so whenever this concept is starting in your class, we will do. Till then we will not do anything in the software class. Sir will engage the class, I think. Okay, so you can now ask me if you have any doubt, otherwise we'll close the session. Sorry, one more thing I need to explain actually. In class before the last class, I think last class, there was one confusion. I could not explain the drift criteria, how to check the drift criteria, so let me explain that also. So there I told, if suppose you have your structure like this and you are pushing by some force, and accordingly you are getting some displacement, let's say delta. Okay, so this now suppose before running this analysis you have designed this structure. This structure is designed for VD, design base shear. So this VD is obtained by using this Z by 2 into I by R SA by G into seismic weight. Okay, so your structure is designed to resist this base shear. Okay, so after designing, now you are running, let's say, pushover analysis. Lateral force means this is pushover analysis only. So after running the pushover analysis, sorry, not pushover analysis, response spectrum analysis, say. So we have analyzed the structure for response spectrum analysis, and we have observed this delta. Now you have this H, we have discussed in that class. So depending on that, you can determine your drift ratio, delta by H. Okay, this I said you have to compare with the limiting value given in the code, which is 0.04. so less than or equal to, you can say less than or equal to 0.004. okay, here we had the confusion in the last class. I told you have to multiply this with 5 actually, which is not true. You do not have to multiply with 5. Instead you have to check for 0.004 only when you are performing the response spectrum analysis or equivalent static method. Okay, it means when your structure is designed for design base shear of VD, then the drift ratio which is obtained should not exceed 0.004. okay, the drift ratio which is obtained should be less than this. Now suppose I want to check for other case. This I have satisfied. Let's say when I check this base drift ratio, this is satisfying the criteria. Okay, now you are going to analyze the structure for pushover case, let's say. So you can again check the drift criteria, but that should not be satisfied with this value in case of pushover. Then let's say I want to analyze the structure for time history analysis, means I want to apply the real earthquake here. I want to apply the earthquake, let's say something like this. I want to apply some earthquake, I'll apply here. Okay, and I'll analyze the structure for this real earthquake, and I'll again check this. Okay, but in this case also this will not be 0.004. What will happen? When you are running time history analysis, let's say time history analysis or any nonlinear dynamic analysis, time history analysis THA. So in this time history analysis, that delta by H, now it should be 0.004 multiplied by 4, sorry, multiplied by 5. Okay, so this is 0.02. This is because in case of time history analysis, we are considering the full nonlinearity of the structure. Okay, we are not relying on the reduced base shear. This VD is actually reduced base shear. As you can see, this is reduced by the factor R. Okay, but in case of nonlinear analysis, we are not considering the reduced base shear, we are considering the actual base shear. Okay, so if you remember the equal displacement principle, you have one hypothetical structure which is linear elastic, and you have the real structure which is not fully linear. So this is our real structure. After reaching the yield base shear, then it will go to the plastic region and it will reach to the maximum displacement. Okay, so this is the maximum displacement delta max. Now according to the equal displacement principle, the maximum displacement which can be obtained by the structure is equal to the max displacement which is possible also by the hypothetical linear elastic structure. Okay, so for this reason this criteria is valid. Okay, initially we consider the reduced base shear here, PD. This is the reduced base shear, and the displacement what we obtain for reduced base shear, this we check by 0.004, only this first part 0.004. But when we consider the nonlinear time history analysis, you do not consider your structure reduced base shear case, you consider full hypothetical structure, means full nonlinearity you consider. Okay, but as you see, the maximum displacement is same in case of both hypothetical structure and actual structure. Okay, so because of this you have to check for the total displacement what can be obtained, not this reduced displacement. Okay, so this is the total displacement which can be obtained, and this should be checked for this limit. I think this is a bit clear to you, not fully I think, but you if you think on this, you will have some idea. Okay, so just think about this, and if you have doubt, again we can discuss in next class as well. Okay, so hinges first before defining. Okay, Akshay, can you actually I didn't get your question properly. We have assigned the hinges first before defining it. Can you clarify your question? Actually I didn't get properly.
Sir, while modeling, we have first assigned our hinges
Huh?
to the building. and
uh,
haven't defined it. Why so?
okay, actually, yeah, as I told, there is two possibility. One is the hinges by default, which is provided by the software to go for it instead of defining our own hinges. Okay, and another way is instead of defining the default hinges, you can define your own hinges. Okay, let me show once again how to define the hinges, then it will be clear. First I'll delete the hinges which is already defined here. Select all the columns, delete, then select beam, okay. Okay, I think we do not have any hinges now. Now see, there are two possibilities. One is to go for the default hinges provided in the software. Another one is define your own hinges. Okay, so if you want to go for the default hinges which is provided in the software, then you do not have to define your own hinge. Okay, so in this case what you do, we select the member where the hinge is to be defined. For example, I want to define the hinges for beams, so and select the beams where you want to define, then go to assign frame hinges. Now here you see auto hinge is selected, means I am not defining my own hinge, instead I am relying on the software. Here you can choose the point where you want to define your hinge, then add, and here you select the code and concrete beam. Okay, so M3, and here you select the load case and other details what you want to select. Okay, similarly at any other point where you want to define. So this is by using the default hinges given in the software. Okay, this is one possibility. Another possibility is you first define your hinge here. You define new property, then name beam hinge or anything, something whatever you want to give, then M3, and here let's say I want to define these values, anything, so let us keep these values which is given here. Okay, now this is my defined hinge, this is not the hinge given by the software, this I have defined, and I want to assign this hinge now. Okay, so again go to select, object type, beam, select, then assign hinges, and here I'll select that beam hinge what I have defined, and let's say this I want to define at 95% relative distance, and add. Okay, see here in this case if I click on this add, that another window is not coming where I am selecting the code book and all, because all the details what was necessary already I have defined. Okay, so directly it is adding now. Okay, so the hinges are also defined, as you can see new hinges are appeared here. So these are the two possibilities how you can define your hinges. Now you can tell whether your doubt is clarified or not. Akshay? Okay, so I think your doubt is cleared. Any more doubt? Anyone else? Okay, so if not, we'll close here, and still if you have any doubt, you can let me know in the WhatsApp. In the next class we'll discuss if you have any doubt. Okay, so we are closing here. Okay, thank you everyone.